करते हैं. We have talked about different types of works. जो when we were talking about heat, I said कि वो conduction, convection and radiation वो formula आप कर लीजिएगा. That is enough. And when we talk about work, there are different types of work. And idea was just to refresh your understanding and just to highlight that these are the types of work. Okay, so you should not get confused. कि जैसे surface tension का work है, strain energy है, all those things are there. Electrical energy is there, electrical work is there. So you must know all of them. Okay. Now we are talking about expansion work. Now, expansion work is when the system is expanding and it is prohibited externally by pressure, surroundings pressure. So some work is being done. Now here the basic mistake is done, and the basic mistake happens that what we are being taught is basically a formula that P is equal to dV. That is what we are being taught. But actually, when we do the work, then the transfer of work depends upon what is the opposing force. So unless until there is a force to accept the work, then you cannot do the work. Just for example, I take a duster here. Now, if I am doing work on this, I am doing work against gravitational force, right? So howsoever whatever force I apply, the work actually done will be against the gravitational force mgh. Similarly, in case of spring, whatever force you apply, the energy stored in the spring is half kx square. And if you do more work, it goes into the kinetic energy of the mass. Okay, so one should know that how the work is being transferred. So we are talking about the transfer of work from system to surrounding. That is the we have to find out. If the system is doing work on itself, we are not bothered. Right? What we are looking for is what is the work done by the system on the surrounding. And then we have to take this formula that what is the external force and multiplied by dot product by dr, integral it, and you will get the work done. Now that can, in case of volume, it can be written like P external into area into displacement, or you can write P external into dV and integral it. Now the thing is that depending upon whether your process is quasi-static, if your quasi-static process is there, then what will happen? Your P inside pressure is equal to external pressure because it's a very slow process. This is the assumption you make for quasi-static process. And that is why you can replace P external by P dV, and this is how you get the formula. So whenever you are using the formula P dV, which assumes automatically that the process is quasi-static. But if the process is non-quasi-static like this, you have to use this formula, P external dV. Now that's a different thing, that whether you know the external pressure or not. If a question comes to you and I give you a question, one of the answer of the question is that the question cannot be solved. But if you solve it wrongly, then negative marks. And if you rightly say the question cannot be solved, you get full marks. Right? So our understanding should be clear. So if P external is not known to us, we cannot find what is the work done by the system on the surrounding. Simple, leave it there. We should be confident that it cannot be done. But if we want to find out what is the work done by the system on the surrounding, then we should know P external into dV integral, and we can find out. Only in case when it is a quasi-static process, then you can say you take internal pressure P dV, and do it because they are equal. Okay, so this thing shall actually sit into your mind perfectly. Now I am taking this example. We talked about this last time also. We have a here piston and cylinder system. Inside pressure is P, outside pressure is P external, right? And then what is actually happening? Now, if P is not equal to P external, now what is going to happen? Depending upon which is more, if P is more, right, what will happen? Your piston will move to the right, or if your P is less than P external, the piston will move to the left, right? Now you can see the work done by the system would be equal to P delta V, work done by the system. But work done by the system on the surrounding is P external dV. Okay, so there is a gap. If these two are not equal, in a quasi-static process, both are equal. So work done by the system is same as the work done by the system on the surrounding. But here they are different. Now what happens to this difference in work? P minus P external to delta V. What happens to this? Now this work actually goes into piston, molecules of the system and molecules of the surrounding as kinetic energy. If your internal pressure is higher, the external pressure is lower, there will be a jerk. There will be a significant velocity. It will not be zero velocity, right? Because F is not zero. F is equal to ma. You will get acceleration. Your piston will be accelerated. So part of the energy will go to piston, part of the energy will go to the molecules which are resisting it outside, and part of the energy will go to the inner molecules also, because when the piston drags like that, just like suppose a piston moves like this, behind it the molecules will get accelerated because of vacuum it will create. Okay, so the energy is going, this difference in energy is going to the molecules of the air system, of the surrounding, as well as to the piston. Now what will happen to the piston? Piston doesn't keep on moving continuously. Piston will stop, right? You can have those systems, but those will be different types of problems. At the moment we assume that the piston has stopped. Now what has happened? If the piston has stopped, its kinetic energy is gone. Where that kinetic energy is gone? That kinetic energy dissipates due to friction as heat to the piston. Now piston is getting heated up. Now that heat is again finally goes to system and surroundings, right? And the remaining part, kinetic energy of the piston, goes into the molecules of the system and the molecules of the surrounding. So this is what is happening. Your piston is getting heated up, your molecules are getting accelerated, and inner molecules also getting accelerated. So everything is getting energy. That is the surplus work which the system did. Okay. Now what happens to the kinetic energy of the molecules of the system? That dissipates and gets converted to thermal energy. It's something like that. Suppose your fan is moving there, it is rotating the air, it gives them kinetic energy, but after some time what happens? That kinetic energy gets dissipated as thermal energy into air itself. So whatever the molecule, you have kinetic energy of molecules, right, that get distributed because of collisions between them within the system and in the surrounding. So finally what has happened? All the extra work which you have done has converted to heat. The kinetic energy of molecules got converted to thermal energy from both sides, and the kinetic energy of the piston got converted to heat due to friction. Okay, so all this thing will happen, but How do we do the problem then? Because this is doing the perfect analysis, going far too deep, right? Of course, you can do it. There is nothing wrong in it, but then you should know all the details of this. So people have not looked into it and they have not developed problems based on this. That what is happening. But you can easily develop with some. But now what happens is that we normally ignore dissipation of extra heat and work done by the system to the surrounding and the piston. So what we do is we assume that all the work done by the system is remains with the system itself, extra work. So what is happening is the work which is going out is P external delta V. That goes out and that has to be accounted for because thermodynamics means heat and work transfer between system and surrounding. So you should know what is the amount of work has been done on the surrounding and that is equal to P external delta V. And all these energies which I talked about, traditionally we take it that it remains within the system as thermal energy. Okay. Now, if somebody tells you, no, this doesn't happen, yes, this doesn't happen. It goes to all the places I told you. It goes to the piston, it goes to the surrounding, it goes to the friction. But then you should have data for that to account for that. Otherwise, you can simply say कि ये होगा, ये होगा, ये होगा, ये होगा, and the problem is you are not able to solve the problem because details are not given. Okay. So if you assume, if it is not given that how much of energy is going as thermal energy to the piston, to the surrounding, etc., then you are well within your right to assume that the work transfer is only P external delta V, and whatever P dV, if you can think of, it is remains with the system. Okay. So even if the system has done extra work, more than what has gone to the surrounding, the remaining work remains with it and it gets degraded into thermal energy. Okay, because its pressure is lost. इसका pressure कम हो जाएगा. तो ये जो है हमें इस तरीके से we have to solve this problem. Okay. Then there is one more thing is that suppose this is called partially free expansion. We call it as a partially free expansion because the outside pressure is less than the inside pressure. So it will expand up to some time freely. After that, it will stop when the inner and outer pressure will be same. But there is something called free expansion. That means there is nothing outside. The outside is vacuum. If outside is vacuum, the work done by the system on the surrounding is zero. So if you take a case where P external is zero, and I tell you the piston has moved from place 1 to 2, that is volume has changed from V1 to V2, what is the work done by the system? Zero. It cannot be P dV or P delta V. It cannot be. Okay. So you have to take this thing account. And this is where normally people make mistake. And this is what is not mentioned in the books. Okay. So you have to be careful about it. Now we move to the normal solutions where we are talking about quasi-static and isothermal. So when you say that external pressure is same as the internal pressure, and we also put a condition that it is the isothermal case, that is PV is equal to constant, you will get the formula that work done is equal to P2 V2 into ln V2 minus V1. This you can derive yourself. I am not deriving it. Not only thing is I start with P external dV. That is the standard work done on the system surrounding. Then I convert P external to P because it is a quasi-static. Then I put the equation that PV is equal to constant and solve it. Okay, you should be able to do it. Okay. Then if you talk about polytropic process, again our P external is same as P internal, and PV raised to power n is constant where n is not equal to 1, because if n equal to 1, it is an isothermal case we have already considered. If n is not equal to 1, you can solve it, integrate it, and you will get these relations. There are three relations like this. They are come from each other. There is nothing special about it. Mathematics only. So first is P2 V2 minus P1 V1 divided by n minus 1 and negative of that. Then you can replace P2 V2 by nRT. You get this equation, and you can write in terms of mRT also if you want same thing. Okay, depending upon how your R is specified. If R is specified in moles, you will take nRT. If it is specified in kg, you will take it as mRT. Okay. हाँ नेगेटिव आना चाहिए. You are right. तो लगा देते हैं. Thank you. Okay. And then if you have a free expansion, that is we have already talked about, it will be equal to 0. Okay. Yes. किसमें? हाँ हाँ. नहीं, that is what I told you, that we are this is what actually happens in real life, है ना, वो सब होगा. But unless until the problem specifies, how will you find out? So will you stop at this P external dV, उससे हम निकाल लेंगे. That's all. Then it is the responsibility of the person who is giving the question that he gives the detail कि भाई कितना एनर्जी किधर गया, कैसे गया, वो सब बताना पड़ेगा उसे. Otherwise, how will you solve it? ठीक है ना? तो normally people don't venture into that. That's being more of theoretical. और जब आप प्रैक्टिकल प्रॉब्लम करेंगे जो कि then one has to talk about that. How much energy is going where? क्योंकि जब आप एफिशिएंसी की बात करेंगे, when you will try to minimize that, तब ये चीजें आएंगी. Actually, these are more of a theoretical nature because closed system पे we do not do much work. Practical. Because all machines are open machines, open flow machines, or open system. So actual problems come from the steady flow energy equation, not from this. This is just to understand the whole thing. Okay. Then partially free expansion, I have already told you, explained in detail. It will be. Now then there is one more thing, that you can understand expansion work as area under the curve. Now for that again, it should be quasi-static expansion, because we are talking about PdV. Okay, so okay, in the expansion work we will be talking about PdV. Okay, the moment we say it is quasi-static. Okay, so because here your P is equal to P external. So we are trying to solve this not mathematically or algebraically. We are trying to solve it by graph. Now PdV जो है, that is area under the curve. You can see that. But before that, let us draw these equation. ये तीन curve I have drawn, and rather there are 5. Plot for PV n equal to constant. This polytropic process. If you draw like this horizontal line is n equal to 0, vertical line is n equal to infinity, and you have these three lines A, B, and C for which n is different, and it is like this. ये जो है, which one for what is the n value? You can see that n is increasing like this, and from n0 to n infinity. So n for curve C will be smaller than B, that will be smaller than A, and A is smaller than the vertical line. Okay, this is how. So if you have to draw two lines of different n, right, just do it graphically. You know how to draw the lines, because exact lines आप नहीं draw कर सकते, because unless until you make the calculations for each value of n, you have to take 5-6 points and then draw the line. But actually conceptually you can draw it that the line which is having more n should be towards the left if you are starting from the top. So you are starting from the same point P1, and if you are going down, expanding up to same pressure P2. So you start from same pressure, you start from end at same pressure P2. Then the PV raised to power n is equal to constant, where n is more, then you will be more closer to vertical axis. Okay. And this you can prove also that we know that P1 V1 is equal to, this is the relation for polytropic process. These are, I am giving you tips how to understand the problem or capture the problem, right? Mathematically, so you can do it, there is no problem. But some shortcuts, how to. So P1 by P2 will be equal to this, and from this you know that 2A is less than 2B is less than 2C, which means that Na should be greater than Nb should be greater than Nc. Okay. Now when you talk about this, so expansion work is PdV, that is area under the curve. But you have to remember one thing here, that when you are saying that the area under the curve, the diagram is PV diagram, right? You can't plot anything else. P has to be on y-axis and V has to be on x-axis. You cannot do it otherwise also. You can't put V on the y-axis and P on the x-axis and say that PdV. No, that is not permitted. So that care also you have to take in one side. And further you have to say that physical unit of area on this diagram is PV. So the unit of the area is valid for all the problem. When area under the curve, what is the unit of the area? Because if the problem is that is simply mathematics problem, so area is meter square, centimeter square, whatever it is. No. Your x-axis is having some unit, y is having some unit. What is the area under the curve? Multiply units of y-axis with the units of x-axis. That is the unit of area. So P into V is actually unit of work in joules. If your P pressure is in Newton per meter square and volume is in meter cube, you will get joules. So this is the you have to take care of. So if a isochoric process hai, so you can simply find out from here area under the curve. It will be 0. तो बहुत सारे प्रॉब्लम्स ऐसे हैं जो कि एरिया अंडर द कर्व में इजीली सॉल्व हो सकते हैं. If you talk about isochoric process, that's the simplest of that. Your dV equal to 0, work done is 0. We are not using PdV equation. We are just saying area under the curve. Now let us take another. If pressure is constant, you get this equation. Work done is equal to PV2 minus V1. Simple. So you don't have to remember any formula. You just find area under the curve. Then, if you have this, now see this equation. Now here pressure is directly proportional to volume. Okay. or you can say there is a linear relation between the two. Now, if you use that relation, whatever relation is here, and if you use that to find out this PDV integral, it will take a lot of time to solve it. But here you can simply find out work done is equal to P1 plus P2 multiply V2 minus 1 half area under the curve. So the idea is to tell you that this is also an option. It's not that PDV, that doesn't mean that PDV is giving you wrong answer. It becomes slightly lengthy. Sometimes this is easier. Okay, that's the only thing. Okay, now then final statement about it, that about the first law, what we have done is for closed system, whatever we have studied so far on the first law, it is valid for closed system only. All the equations apply to closed system only, or we can say non-flow system. Okay, and we can apply freely to such system, but when you will talk about open system, then we will do it separately. वो next हम उसको करेंगे, ठीक है. तो और meanwhile जो है मैं आपको ये कुछ steps और बता देता हूँ, steps to solve the problem. ये it's applicable to any problem, any engineering problem. Now this will make your slightly आपको लगेगा कि इसमें ज़्यादा टाइम लग रहा है. The way, if you follow this way, you will find that you are taking more time in solving your problem. But it's something like this कि वो जो hare and tortoise की race है ना, the one who runs faster also sometimes topples, वो गिर भी जाता है. तो हमें जो है क्या कहते हैं, we should follow a particular procedure for doing it. The advantage, as I told you, that if you are 100%, if your problem by mistake, even if you know and you have done wrongly, then you are stuck up. Then you are lost, in fact. Not only the problem, the additional cost of that of not doing another problem. Okay. तो आपको सबसे पहले क्या करना चाहिए, आपको स्केच बना लेना चाहिए प्रॉब्लम का जो भी है, and you should note down all the information given in the diagram, like state of the system, process, etc. on the diagram. Okay, what you are doing is the information which is giving in the form of sentences and parts, that you are putting in a photographic image, and that perception, you are able to comprehend the problem as a whole, not in parts. So that helps. तो आप हमेशा, whenever you are doing any problem, make a diagram of the problem, put all the information which is there in the question on the diagram, okay, whatever conditions are there, and double check it that what you have noted is exactly correct, and then leave the paper aside. Okay, because any mistake at any step will actually lead to the final answer being wrong. So you have to be very careful when you take down the question on the paper, make a diagram, put all the information correctly. Then you should also see what are the laws it will apply. What are the laws which can apply to it? You should put them, those laws. So, and then these laws will actually are the governing equation, which will govern that equation. And the next step is, this is that you have to list all the unknowns, that what are the unknowns in the system. Okay. Now then you have to check whether the number of unknowns is equal to the number of equation. If this is true, that means you have put the problem properly on the paper, you have written it, understood the problem properly. The rest is mathematics. what do? You understand a problem, put equations, convert it into equations, and solve that. But what you have to see in between is that when you are transferring a problem into equations, you should be correct. You should have taken all the data. And then once you have written the equation, before solving the equation, you should know that you have sufficient data here. That number of unknowns is equal to the number of equations. If for any reason number of equations are not same as number of unknowns, then go back. There is no way you can proceed. Unless until your equations, number of equation is equal to number of unknowns, you cannot solve the problem. Standard rule है ये तो. So once you are sure कि हाँ equations सही हैं, unknowns भी सही हैं, then you solve the problem. So this is technique you should adopt. थोड़ा practice करें धीरे धीरे, at least in the room you can do it. You will find that it is helpful. ठीक है? When you are doing your problem, and especially I have given you assignments also, when you do that assignment, try to do it that way. Okay, this will be it. So we will stop here, and now next topic would be application of first law to flow processes. Now the importance of this topic is, as I told you, that yes, closed systems are not much in use, because you want a cyclic process. You want, because the whole objective of mechanical engineering, or at least the this thermodynamics, is to get work from machines or engines. So you have engines, you get work done, but you want continuous work. You don't want work for only for some time and then leave the system. That would be no good. So जो flow system है जिसमें continuous आपको work मिलता है, that is what is the heart of this, you can say, your mechanical engineering engines, right? At least thermal engines. तो ये जो है टॉपिक उस पर कोरिलेट करे. सिंपल है, ऐसी कोई दिक्कत नहीं.